And when I was a student in physics, I had really difficulty in understanding what quantum mechanics was about. I was very curious and attracted by the challenge of understanding that theory, because when I was a student I really could not make any sense out of it. So then I decided to to work in my thesis work to be in a foundation of quantum mechanics, because I was thinking that there was something that I could not understand. So that's how it started when I was quite young. Third year of university, yes. And working in, at the beginning I was thinking that the problems was with the difficult mathematics. That's why I started more as a mathematical physicist, because I was convinced that if one could understand the mathematical structure of quantum mechanics, could understand also the physical meaning of a theory. But then in the years I realized that that was not like that. I mean, there was more than just the need of mathematical clarity. There was a need of conceptual clarity for really understand what is the picture of the world that quantum mechanics is giving to us. Now the main problem is this, that when you study classical physics, classical mechanics, you have an idea of how looks the world according to that theory. It's quite simple, and the same electromagnetism. But as soon as you go to quantum mechanics, the main difficulty is that you don't have any grasp of how could be the world according to that theory. So that's the challenge that still continues.
Yeah, thank you.
Quantum mechanics is the best theory we have to understand what is going on in the microscopic world. The main difficulty of understanding what is going on in the microscopic world is because the microscopic world, the world of atoms and what there is inside the atoms and what there is inside the constituents of the atoms, is very far removed from our experience. All we know is through experiments, through the data that we have, but we don't have any direct access to that reality. So that's why it's very challenging, quantum mechanics, because all we try to do is try to find an order in all the data that we get about that microscopic world, but it's not something that we have direct access to. So quantum mechanics originally was formulated in such a way that the question of what is the nature of the world on the microscopic level was somehow dismissed. Was good already to have a good theory providing predictions for experiments, to give some idea of what there is, but not a very precise idea. And later, it became clear, thanks to the people like Einstein or Schrödinger, that that was not sufficient. So quantum mechanics is difficult because it's talking about something of which we don't have any direct access. And if I understood your question, the question is, what is the theory that I prefer? No, you said that. I prefer a theory which is able to go beyond the appearances, and a theory that is able to tell us what is the image of a microscopic world. I don't want to have the final theory. I'm a scientist, so I know that all theories of the best theories of today, tomorrow will be a change. There will be something else. So when I'm saying that I want a good representation of a microscopic world, I say, given the knowledge that we have today, but like everything in science can change. So my answer that I will give you, the theory that I prefer is Bohmian mechanics. I know this is not definite. I'm sure that in 10 years, in 50 years, or maybe next week, there will be evidence that will tell us that something else is true. But at the moment, why I like Bohmian mechanics? Because it's providing that picture of a microscopic world. Not just simply a picture. I don't want to give a naive idea that if I'm not able to picture it, that doesn't work. But more than that, it's giving us a precise characterization of everything that happens in space and time. And at the same time is in complete agreement with the prediction of quantum mechanics. So it's something that goes beyond quantum mechanics, but at the same time is compatible with the prediction and with the usual structure of quantum mechanics. Is a theory that gives us an insight on what is the microscopic world. And the interesting thing is that the theory that allows us to understand much better than the other theories the true innovations of quantum mechanics. For instance, a true innovation of quantum mechanics is non-locality. Quantum mechanics is telling us that the world is really very different from what is the classical world. And one of these features is non-locality. One of the merits of Bohm mechanics is to make this completely clear, the non-local character of the world. No, I don't think it's special. I think that randomness, even the classical world could be random. There is no such a thing as quantum randomness per se, but there is something related to randomness, which is a property of our world. I mean, what is something that in my work with Detlef Duhr and Shelley Ghost that we call quantum equilibrium, to give an idea of what it is I can say the following. I can say that there is the possibility of understanding why our access to the microscopic world is so difficult, why we can get only a very limited information of what is going on in the microscopic world. This can be made precise, so there is a sense in which we can understand the Heisenberg principle. Usually the Heisenberg principle is considered to capture the quantum randomness, because the Heisenberg principle is telling us that as soon as we try to measure a certain quantity, then there is something else that becomes very much uncertain. Now, in the framework of the theory that I was describing before, Bohm mechanics, is it possible to understand why it's like that? Why there is something like the Heisenberg principle in our world. And it has to do with the global feature of the world in which we are. So it's something very important. So it's not randomness per se, which is the novelty, but it's this fact that our world is such that there is an intrinsic limitation to the possibility of gathering knowledge about all the facts. And that is something that we have to face. It's a limitation which is not due to our technological limitation, it's not due to our poor instruments. What we understand nowadays is that there is an intrinsic limitation on the possibility of gathering, of obtaining knowledge on the world. And that is the true essence of Heisenberg principle. The funny thing is that this can be understood in a theory which is completely deterministic. Bohm mechanics is a theory which is, non-relativistic Bohm mechanics is a theory which is deterministic, but allows us to understand why there is something that appears as a sort of very strong and intrinsic randomness. So I would say that the fact that is deterministic is interesting, but so it's making more dramatic or more curious. I think it's very curious to notice that our understanding of quantum randomness comes to a deterministic theory. At the same time, I don't think there is nothing special about determinism, so I'm open to new formulation of a theory. When the theory has to be extended to the relativistic regime, to general relativity, maybe we have to abandon that determinism. So determinism and randomness are both not spatial. I'm not attached to neither of them, and I'm open to evolution of physics, and to see that maybe tomorrow we need to formulate Bohm mechanics in not in deterministic terms. Actually, we already have something similar to that. Actually, we know now that to have a good understanding of quantum mechanics and special relativity, especially for having a good understanding of process of creation, annihilation, something like intrinsic randomness is needed. So. The implications of Bell's inequality for a physicist are that nature is non-local. And is non-local in a sort of very precise way. What does it mean, non-local? Non-local could mean many things. For instance, could mean that if I push a button here, then immediately in some other galaxy, somebody is able instantaneously to receive my message. This will be a sort of non-local connection between what is happening here and what is happening in another galaxy. Now, the non-locality of implied by Bell's inequality is of a different character. It's not, doesn't have such consequences on our world, of the world of daily life. We know that it's impossible to transmit information, namely I'll push a button and something happened there, and and then I can communicate instantaneously with other parts of the universe. That is not the non-locality that is implied by Bell's inequalities. The non-locality is still an action at distance, but is an action which is not that cannot be used to transmit information. So there is, in a sense, the implications for our daily life are not so dramatic. Basically, nothing changes. But at least what we have is that a perception of a world that is more connected than it is according to classical physics. Is a world in which something happening here can be correlated with something happening there, very far away, but in such a way that no possibility of signaling, of transmitting information, of transmitting energy or whatever is possible. So it's a sort of, it's a very subtle thing. It's something which is completely compatible with our worldview. I mean, the fact that we know that these things are impossible, that it's impossible to do such things. But at the same time, shows that there is some sort of deep connection between distant events, and this connection is exactly the one that is a consequence of Bell's inequality. An interesting thing about Bell's inequality is something that is very much debated in the conference that we are having here in Bielefeld, and something that is not so much appreciated is that Bell's inequality have a consequence that are very general. They imply that nature is local, is non-local. So they imply something very general. They don't have. Sometimes people understand Bell's inequality as being providing a proof, a demonstration that that is impossible to have a description of a microscopic world in terms of stuff that, you know, I will not be more precise than that, but stuff that interact locally. So that's what some people take as the main lesson of Bell's inequality, and this is somehow said, expressed in the form Bell's inequality implies that there are no locally variable theories. Now that's not the main lesson. The main lesson is that the world in which we are is non-local, and so quantum mechanics is non-local. Many people think that quantum mechanics, standard quantum mechanics, can escape the conclusions of Bell's theory, but that's not true. That's what Bell proved quite clearly, and Bell's analysis, together with the experimental results, I mean, since the time of Bell, there have been many experimental tests. One of these tests has been discussed in this conference here recently, just yesterday. Now we are completely sure that Bell's analysis, together with experimental results, provide us with the most convincing evidence that the world in which we are these non-local. In this world, there are these non-local connections, which cannot be used to transfer information, but still are there, and so we are in this world. Difficult question, very difficult one. I could answer, and I could give two answers. The first one is that I think that philosophy should have a little role in physics. The second one will be that philosophy should have a big role in physics. At the end of my explanation, you will find my global answer less contradictory than it may seem. But first, let me give arguments for both positions, that philosophy should play a small role and philosophy should play a big role. So let me explain. When I say that philosophy should play a small role, I mean this. I mean that physics is a human activity devoted to understand what there is in the world, how it behaves, to find this through the experiments and through elaboration of mathematical theories. Galileo Galilei was saying that our understanding of the world comes from sensate esperienze, which means sensible experiences, and certe dimostrazioni, that means certain demonstrations that are certain because they are mathematical. So the major role in physics, in our understanding of the world, is played by experiments and mathematics. So this is what I think should be the essence of physics. So it seems very little room for philosophy. But if one then thinks a little bit more, comes to the conclusion that the certain experience that we make, according to Galileo, we make because we ask questions to nature, because we want to find out what there is. And when we formulate the question, we formulate this question on the light of a certain theory. We have already some theoretical prejudice. When Galileo was making his experiments, he had in mind already that he had already an idea that the acceleration in the gravity field of Earth, that the motion on the surface of the Earth occurs at constant acceleration. But then he was trying to probe nature to see whether that was correct. At the time of Galileo and of Newton and later on, there was somehow the idea that the understanding of nature was mathematical, but before the mathematics there was a clear understanding that physics had to do with an objective description of the world. The world has a certain feature, and mathematics is used to describe what there is. The long tradition of atomism in physics, Newton was an atomist, but then found this major development in the 19th century. People were thinking that the gas in this room, every object in this room, could be made of small little particles moving in the empty space, and by analyzing the mathematical laws that were governing the motion of these atoms, then one could arrive at a good understanding of the macroscopic world. So I'm saying a long tradition in physics was that we start with an objective world that we try to understand. That means we don't put into discussion reality. So in a sense, physics was an attempt to understand the world different from classical metaphysics that was postulating substances, properties, a little mathematics. It was a different way of understanding the world, but still had something in common with classical metaphysics, namely that the goal is to understand the world independent of us, which is there, and we try our best to formulate theories about that world this world and to check this theory by doing experiment. In the 20th century, a different view arose, namely that that is impossible to, was defended the idea that was impossible to have such a direct representation of the world, but grow the idea that for our limited abilities we are not able, we should abandon the idea of describing an independent world. And the argument were based on some experimental evidence, but also on a very philosophical standpoint. So there was this idea that we should abandon the classical view that was considered naive and grows a certain way of doing physics that we may call quantum philosophy. That means this idea that we should allow for the observer. That means that we are describing the role, we are playing a big role in the expression of the laws that are governing the universe. I don't want to enter into that, we'll go too far. So let me summarize by saying that a sort of bad philosophy played a big role in a certain understanding of the moral of quantum mechanics. Since bad philosophy played a big role, now it's time that a good philosophy will play the role to put everything to where we started. I mean, I don't want to go back to the physics of the 19th century, but I want to go back to a certain idea that we attempt to give a description of reality independent of us. And there, I think that philosophy can play a big role. So nowadays, it's normal to have in conference like this one a community of physicists, mathematicians, and philosophers. The idea is to have philosophy playing a role in the sense I was explaining before, just to oppose a bad way of applying philosophy to physics. So in a sense, what of these two different positions I presented, what is the middle way? The middle way probably is this one. The wise one is that there is no really sharp distinction between philosophy and physics, because also in philosophy changed the idea of constructing a metaphysics according to the views of Aristotle, for instance. No, there was been an evolution. Philosophers that do nowadays metaphysics, they use very much physics to do their metaphysics. So today we are in a situation which somehow is very interesting, because we can say that there is no sharp distinction between philosophy and physics, and there are certain problems that belongs more to philosophy, more that belongs to physics, but if the attempt is to understand the world independent of us, an objective world, that to understand what there is, I think that physicists and philosophers can just both give a contribution to this very difficult enterprise. I think that the most pressing problems have to do with the relation between quantum mechanics and relativity. It is true that few people accept the theory that I was mentioning before, namely Bohr mechanics. But Bohr mechanics or other precise formulation of quantum theory, like the theory of Girardi, Riemann, and Weber, they provide a very good and satisfactory, they give us a good and satisfactory understanding of the non-relativistic world. By non-relativistic world, I mean the classical world, the world in which there is space, physical space and time is absolute, and in that framework, Bohr mechanics is really providing a good, NGW and all these other formulations. But let me mention Bohr mechanics mostly because it's a theory that I'm more familiar with. It's providing a good explanation of all non-relativistic phenomena. But the marriage of quantum mechanics and relativity is the true challenge. Is the true challenge for people that are working foundations and people that are doing also normal quantum mechanics. Nowadays, we don't have a good marriage of quantum mechanics and gravity. Gravity was understood by Einstein as an extension of special relativity. Gravity now is understood as having a lot to do with the structure of space-time. So the effect of gravity, and what we experience now in this room, we know that at the end of the day is an effect of a geometry of space-time, which is something surprising. It seems something crazy, but the fact that we are sitting there, and that has to do with the geometry of space-time. But the theory of Einstein had big success in describing the universe as a whole, but nobody was ever able to give a satisfactory theory that would include quantum effects and gravity effects. So that I take as the big challenge. And since biomechanics and other theories like Gerardi, Rimini, Weber, in a sense also many words, are providing a precise description of a world, I think that this challenge should be taken by the people working in this field, because it's not just simply a question of providing new resulting foundations, but I think that the working foundation can finally reach the point in which can reach a larger community, those of physicists that are engaged with similar problems, namely those of having a good theory of gravity, of quantum gravity. And since in the people doing biomechanics or GRW or the theories that I mentioned, have more resources, have a much cleaner theory, then they should try their best to contribute to solve this problem. And it is unfortunate that there are not so many people that are following this way of understanding quantum mechanics, but more people there are, more chances there will be to solve these big problems of having really a unified picture of a world in which we can go from the very, very small, the quantum, to a very big, gravity, the universe, in a very satisfactory and unified way.